What takes place within neutron stars? The issue is that our models have difficulty explaining the severe physical constraints that govern the behavior of matter inside these superdense objects. But what we have discovered thus far is already astounding. How do neutron stars develop? When a massive star exhausts all of its nuclear fuel, its dense core collapses, atoms are compressed by gravity, electrons are converted to protons, neutrons, and neutrinos, and the star's outer layers fall away at a speed of a quarter of light. A supernova explosion results, leaving behind a bare, superdense core that is almost entirely composed of neutrons. As it emerges from a supernova, a proton-neutron star is extremely hot, with an interior temperature of thousands of billions of degrees. The protons inside it start to decay immediately, releasing a massive quantity of neutrinos. When neutrinos leave the star, they take energy with them. The star's interior swiftly cools to around 1 billion degrees, and its outer layer gets much colder. When the star's temperature hits about 500,000 degrees, a solid crust starts to form. The neutron star continues to cool over the following several decades, and after several 100,000 years, it has reached an inner temperature of several 100 million degrees. The hard crystalline crust, which is about 1 kilometer thick, is made of iron, the same material that gathered in the parent star's core before the star's supernova explosion. Why is iron? Because the formation of iron is the final stage of thermonuclear combustion. In ordinary stars, for thousands and thousands of years, hydrogen burns and turns into helium, helium into carbon, and so on. Ultimately, silicon and star ash iron are formed. The idea that the initial outer layer of a neutron star is made of iron came about since it is no longer possible to obtain more energy from the iron core of the parent star. A thin layer of gaseous atmosphere, which ranges in thickness from a few millimeters to around a meter, lies on top of this crust and is controlled by the magnetic field of the star. The revolving star's magnetic field are what propel particle jets into space and, as a result, strong radiation fluxes. A neutron star's crust is a very intricate structure. The physical characteristics of the crust alter as we approach the star's core along with the fast-rising density. The electrons act normally in the outer crust, which is composed of iron crystals. They circle around the nucleus in each iron atom. However, as the density rises, the energy of the electrons rises, and they are pushed into the protons. The farther we move inside the star, the more electrons are forced into the nucleus. When a negatively charged electron interacts with a positively charged proton, the proton turns into a neutron, releasing a neutrino. This process continues down to the point when there are so many neutrons in the nuclei that they start to leak out of the nuclei. The neutron instability point, below which free neutrons start to form pairs that make up a neutron superfluid liquid with zero viscosity, is the transition between the outer and inner crusts. The crust's innermost region, immediately above the outer core, has a density that is roughly 1/3 that of the atomic nucleus's center. Scientists claim that because the nuclei are squeezed so closely together, they can no longer maintain their original structure and start to alter. The nuclei are deformed and float in a sea of leaky neutrons in the inner part of the crust, whereas earlier they were spherical, like meatballs. Scientists refer to this phase state as nuclear noodles because it produces a variety of forms, including tubes, bubbles, and sheets known as spaghetti, gnocchi dumplings, and lasagna based on the shapes they take on. Because of the extreme density, individual nuclei are no longer possible in the outer core, which reaches to a depth of around 9 kilometers. Neutrons are in a superfluid state, akin to superfluid liquids at ultra-low temperatures on Earth, and all matter transforms into a nuclear mucus, a soup of neutrons, protons, electrons, and potentially muons. Due to the extreme density, even if the outer core's temperature is reportedly millions of degrees, a superfluid state still exists. Things get stranger and less clear as we travel closer to the neutron star's center. The inner core of a neutron star remains a mystery to scientists, as is the type of superdense stuff that can be found there. Neutrons, which have remained intact even under high-density settings, are thought to make up the majority of the inner core, according to some experts. Other models imply that neutrons decay into their constituent quarks rather than being maintained in their original form, turning the nucleus into a soup of free quarks. This is the quark core model. Another theory states that quarks regroup and form other, more bizarre configurations like hyperons after being released from bonds within neutrons. These are particles in which one or two of the three neutron-forming quark particles undergo a transformation into the dubbed strange quark. Normal protons and neutrons are formed from much more ordinary, so-called up and down quarks. This matter, however, is entirely up for debate.